It is my great honor to give the presentation here. Thank you for coming, and thank you for listening to my presentation to our work, Assassin, a unified abstraction for architecture simulation and implementation. Maybe you will be curious about the acronym of Assassin. It stands for Asynchronized Semantics for Architecture Simulation and Synthesis. This is actually a spoiler to me, since now you all know asynchronicity is the key to enable such a framework. But before diving into any technical details, I would like to first motivate my work. So this is typically happens every day in every company and in every research group in our community. So I am a computer architect. I have a great idea on the architecture. I tell the circuit implementation team, can you do this for me? With high probability, they will just reject me. They will say, oh no, I do not want to waste any of my engineering effort. What if your idea is a horrible idea? You need to first validate it. Oh, Jian is too successful. Every paper mentions it in this session. And they then need to, and then I need to write some simulation code to model, to study how good or bad my idea is. And after this is done, I convince them, yes, this is a good idea. Implement it for me. Then they implement it for me. Is that all? No, it's far away from all. Then we need to calibrate our simulator. We need to align all the design details. So it's another infinite iterations. And in our venue, actually 1/3 of the paper are on architecture, accelerators and microarchitectures, and they are conducted through the paradigm I discussed just now. And actually, 3/4 of these papers are done by the look at the purple part, are done by the paradigm I mentioned just now. We write a simulator for the performance, and we write some separate RTL for the power and area. They are claiming, oh, we are using two totally different things to describe exactly the same thing. And it seems nobody discussed about the alignment and the calibration between the RTL and the simulation model. So to me, the essential problem is that hardware implementation is too hard. And we are solving a problem by introducing another. The problem is that we have separate implementation and separate teams, and it introduces coordination overhead. So what should we do? An ideal solution is that we should have a unified and easy to program interface for both the simulation and the implementation. This sounds like a magic. But to achieve this goal, to explain how I achieve this goal, let me break this down to two sub-goals. First, the unified, second, the easy. To have a unified programming interface, let's first find some commonality between the simulation and the implementation. And I know everyone here learns computer architecture through this simplest and most classic computer architecture 5-stage pipelining. And if I want to simulate a 5-stage pipeline, typically I will implement an event-driven simulator as shown in the code snippet on the left-hand side, on your right-hand side. We can see that, okay, it's a centralized engine which maintains an event FIFO, and every time I pull an event from this FIFO to execute the stage, and each stage can spawn new events. For example, fetcher spawns decoder, and the decoder spawns executor. And this is a trace of instruction execution and of the pipeline execution. And if I just, rearrange it a little bit, you may say, oh, this is so familiar to me, it looks like the waveform simulation for RTL. This phenomenon suggests that, in principle, we can have a one-one correspondence between the RTL simulation and the event-driven simulation for the architectures, pipeline architectures. So instead of programming the circuits, describing the connectivity across all those components, all those transistors in Verilog, why don't we just focus on the program behaviors and the events, okay? And then let's look at the program behavior of a simulator, how it does. So our insight is that it can be perfectly handled by asynchronized event, asynchronized function calling. To explain what is asynchronized function calling, say, okay, I am an instruction fetcher. I fetch the one instruction from the instruction buffer, and I use this instruction as a parameter to call the decoder. But conventionally, in a conventional function call, what happens is that my program counter jumps to the callee, and after finishing the callee, I return this program counter to the caller. However, if we do this in hardware implementation, it will be totally wrong, right? What happens is that we want some asynchronicity or some delay. Otherwise, we will have a too long critical path in our implemented hardware. So my point is that this thing looks so similar to the asynchronized event handling in JavaScript, if you are familiar with some front-end development. Decoder says, fetcher says, oh, can you decode my fetched instruction? Decoder may say, I will do it, I promise. And this is actually what happens, what we do in JavaScript. Instead of returning the result itself, it returns some handle to me, some handle object, which is a promise. And so our this is our basic programming paradigm. So we describe the functionality of each pipeline stage in every single function, and each function is connected by asynchronized function call. And after the calling, we have a bookkeeping that keeps, okay, this function is called, and which will be executed no earlier than next cycle. And by doing this, another benefit is that we have a clear boundary between the conventional and the sequential logic. For all the expressions that takes effect immediately, they are conventional. And for all the instructions that causes some side effect will be categorized in sequential. And is that all? Since the whole thing is suggesting that I am transplanting some software engineering concept to hardware engineering. We find that, there is a fundamental issue in software programming and hardware programming. The problem is that in software programming, when I call a function, all the arguments I feed to the callee are in the same scope of the caller. However, in hardware, this may be not true sometimes. Consider the systolic array, which is the simplest data flow architecture. We can find that PE3 flows data to PE2, and PE1 flows data to PE2. And the problem is that no processing element can call the PE3 alone. So my proposed solution is to bind the data flow. And there are so many binds in this word. And specifically, I'm mentioning this bind, which is known as bind in Haskell and known as a partial function in Python. What it does is that, say, first I define a function with 2 parameters, and I invoke this API. This API binds the first parameter of this function to 5, and return me a new function with a new function signature. When calling the new function, it's equivalent to call the original function with the first parameter already assigned to 5. By doing this, then we can construct this systolic array friendly. When in a friendly way. So when constructing the PE3, we bind the auth input of PE2. And when constructing PE1, we can use PE1 to call that bound handle, so that we can have this systolic array constructed. This is the top function, something like a top function. And finally, we come to the code generation. Surprisingly, under this asynchronized paradigm, code generation is kind of trivial. We don't have that many things to talk about, so I just talk about several runtime and microarchitecture support here. So for the simulator generation, I separate every cycle into two halves. The first half does the combinational logic that will take effect immediately, as well as recording the numbers I'm gonna write to the registers. And those changes will be committed in the second half so that the result can be visible to the next cycle. And with regard to the RTL generation, as I mentioned just now, all the expressions in the function take effect immediately, so they can be just synthesized into combinational logic, which is trivial within one stage. And one of the additional microarchitecture support I added here is the SM, state machine, which is essentially a counter. When the function is called once, this counter increased by 1. When it is executed, it decreased by 1. Every cycle, we just check if this counter equals to 0. If so, we just skip it. If yes, we activate this pipeline stage. And after doing this, let's see some results. So for the left-hand side, the 3 clusters, they are handcrafted. Our framework are comparing against handcrafted designs, a single-issue 5-stage pipeline CPU, a systolic array PE, and a priority queue. And we can find that our designs, our language saves by mean 64% of the lines of code. And this is very useful, since if you all learned the software-hardware interface, the haptics of that book, I remember in the assembly section, it says that a programmer can write the same lines of code every day, no matter it is assembly or C code. And a line of C code can be translated to up to 20 lines of code, or 20 lines of assembly, which means that their productivity is increased by 20 times. We are a start, so we maybe only improve the productivity by 50%. And the second are 5 workloads from Max2Eat. And we can find that, okay, it was unimaginable we can implement 5 different ASICs during the paper deadline, but now we can. And it achieves 1.2 more lines of code compared with the high-level synthesis C code. Note, they are writing C code, but we are writing something that can target to a real hardware. And with regard to the hardware quality, in terms of, you can see the priority queue and the CPU, they are around 1. So, which indicates the power area of our, the area overhead of our language is very, very small. And for the systolic array, it's a little bit awkward because we get the systolic array baseline from Gemini, and their systolic array PE is slightly more complicated than mine. They integrated some activation function into every PE that introduces array overhead, but ours only has 1 MAC. And for high-level synthesis, you can see that we get, by mean, 6 times the performance per area. This is because high-level synthesis has its own fundamental overhead, but we are achieving some near handcrafted performance. And finally, we come to the simulator performance. So with regard to the simulator performance, for CPU simulation, we achieve only 1.5x speed up. And for ASIC simulation, we achieve up to around 6 times speed up. The problem is that within the scope of each function, we have within the scope of each function, within the scope of each function, we can skip the functions are not called in this cycle. So we skip a bunch of instructions. We skip in the granularity of a function. However, in RTL, in RTL simulation, mostly, I know, mostly they are simulated, they are checked 1 by 1. And in CPU simulation, the problem is that every cycle, every stage is busy. And finally, to conclude this work, and beyond the scope of unifying the simulation and the synthesis, I want to say that our language is a first step to invent a so-called C++ for hardware design and implementation. So before, all the hardware description languages, either it's low level but general purpose, or it is high level but domain specific. And here I want to say our language occupies a very unique position, is that it is both domain specific because it is targeting hardware design and implementation. On the other hand, it's also general purpose in terms of the target pipeline architectures. And thank you for listening. All the questions are welcomed. Our infrastructure are already available on GitHub, and you can also scan the QR code to get the GitHub repo. Thank you.